Hello and welcome back. Today we're going to cover section 5.1, logarithms and their properties. You should be working on project 2, which is due in a couple of classes. Quiz number 2 is happening next class. It's on classes 4, 5, and 6, which is all this material right here. So beginning here with the class notes. Number 1, in this section we review a really important family of functions called the logarithmic functions. You may have seen these introduced as the liftoff function if you took college algebra, Math 107 at GCC. 2, the common log, which is log base 10. Log base 10 of x equals log x equals p means 10 to the p equals x. A lot of crazy looking symbols in there, but here's what it means. If you see log base 10 of x equals p, all of those symbols together, I'll put a double arrow here because they mean the same thing as 10 raised to the p equals x. I think of this as just being kind of like a football diagram I have to follow. Take that guy down there, raise it to this power, copy the equal sign, and then write that other symbol. 10 to the p equals x. The common log is so common because, or we call it the common log because it is common, and we're kind of lazy. So instead of writing log base 10 of x every time we want a common log, we're just going to leave that 10 off. So if you see a log with no base there, it is assumed that it's going to be base 10. And next part, the natural log, which is log base e. Log base e of x, instead of writing those symbols, we're going to write ln of x, but I'll write them with the traditional symbols first. Log base e of x equals p. It's the same thing. You're still following the same football diagram. This guy raised to this power, copy the equals, and write the other symbol. E to the p equals x. But again, we're going to be a little bit lazy here. And instead of writing log base e, because that base is really, really important for us, we're just going to write ln x. So if you see ln, it's implied that the base is e. If you see log with no base, it's implied the base is 10. ln stands for logarithmus naturalis, natural log, but in Latin. Number 3, for example, log of 1,000 equals 3, since, and then here I'll write in the invisible 10, 10 raised to the third power equals 1,000. Also, ln of e to the negative 2, I'll write in the invisible base there. E raised to the negative 2, does it equal e to the negative 2? Sure, it does. Number 4, try these by hand first and then verify them on the calculator. So go ahead and pause the video and see if you can do A and B without the calculator and then type them both into the calculator. Okay, for the first part, we're looking to take 10 and raise it to some power to get 0.0001. 10 raised to some power is 0.0001. Okay, it's going to be a negative power. We just got to get the right negative power. Is it 4? So if we put a negative 4 there, it's either negative 3 or negative 4. It's late. I'm having trouble. Let's see. 10 to the negative 1 means 1 over 10. Okay, so that means that when the power is 1, there's 1 0 down there. Okay, I think we're good there. That's negative 4. And then ln of e to the 5th. Again, I'll write in the invisible e. E raised to some power is supposed to equal e to the 5th. E raised to something equals e to the 5th. Well, when you write it that way, it becomes pretty apparent that this is 5. So the calculator knows both of these things. So let's make sure we know how to type them in. So the first one is log of 0.0001. So you have two log buttons there. Log is the common log, that's this button, and then the natural log is this button. Log of 0.123, and then a 1, and we get negative 4. And then if we do ln of second e to the x, and then negative 2, it's, 5, and we should get the 5 that we wrote down up above. 5. Estimate the value of log 157 by hand, and then find log 157 on the calculator. So you're going to pause the video in a moment and try to do this one by hand before you touch the calculator. The idea here is to, again, write in the invisible base. So this is saying 10 raised to some power is supposed to equal 157. Now, the power in question here is not a very nice number, but you should be able to say something. Is it 1 point something, 2 point something, 3 point something, 4 point something? Is it negative? Is it big? What is it? So see if you can give an estimate and then type it into the calculator. Pause the video and come back when you're ready. Okay, so hopefully we figured out that log 157 is definitely between, let's see, so if it were 10 to the second power, that would be 100. That's too small. But 10 cubed is 1,000. That's way too big. So it's going to be between 2 and 3, probably closer to 2. So the calculator can handle this one as well. So we type in log of 157, and we should get 2 point something, about 2.2. So even though you've got that button on the calculator, until you're really comfortable with this idea of logs, I would encourage you to try to not use the calculator the first time you see a new log. Just try to spend a little bit of your time estimating these logs, gain some comfort with them. You should be able to say things like, oh, this is 2 point something, or this is 3 point something, or this is negative something. I think that'll really help and take away some of the mystery that a lot of students have surrounding logarithms. 6, there are many properties of logs, some useful, some not so much. So I've written a bunch of the properties for the common log in the first column, and we're going to fill in the corresponding properties of the natural log on the right-hand side. So in part A over here, it says that log of 1 is equal to 0. You should think about why that's true. ln of 1 is also 0. Part B, log of 10 is 1. You should think about why that is true. It turns out ln of e is also 1 for the same reason. Part C, log base 10, or log of 10 to the x is just x. Similarly, ln of e to the x is just x. I'm not going through the rationale for these properties, but you should be able to understand why those first three properties are true. A, B, and C should be clear if you think about them. Part D is the first one that I think really probably shouldn't be clear. Log of a times b is equal to log a plus log b. I'm not going to go through the derivation for why that's true, but it really just has to do with properties of exponential things, and you know lots of properties of exponents. So there's a corresponding property for ln. It says this is really ln of a plus ln of b. And then there's this nice kind of analogy. If multiplication turns into addition, then division probably should turn into subtraction. Little typo here. So in the second part, we've got ln of a over b. That's really ln of a minus ln of b. Part F, I think, is the most useful property for our purposes on this whole page. It says if you have log of something to a power, you get to take that power and pick it up and move it down into the front. Bring that p into the front, it becomes p times log of x. Same thing over here. Take the power, move it to the front. You don't have to write the dot for multiplication, but I just want to highlight its times. And then part G says that 10 to the log x equals x. That's kind of weird. E to the ln of x also turns out to be x. Okay, so we're going to use a lot of these properties. Let's move on to the next page. I'll also highlight at this point that there is a reference sheet about exponential and logarithmic properties, and most, if not all, of those properties are on the reference sheet, and you will be able to use that reference sheet on the first test. So the reference sheet is located in the reference sheets folder up on our Moodle page. 7, we will make use of these properties when we solve exponential equations. If a county has 40,000 people and the population grows at a continuous rate of 1.3% per year, when will the population reach 50,000? How about if that's compounded annually instead of continuously? Okay, so we will go to our basic continuous formula. So our continuous formula, whenever I see that word continuous, I think part. Usually that applies only to money, so we're going to use the equivalent form. The letters that we had were, I think, a e to the kt. So we fill in, A is the initial amount, that's 40,000 people. K is the continuous growth rate, it's given, 1.3%, but we gotta make sure we write it as a decimal. T is just T. And I wanna know when the population will reach 50,000. So we're gonna take that and make it equal 50,000. Now, up until this class, the only way we were able to solve an equation where the variable is in the exponent was to graph both sides and intersect on the calculator. But using the properties of logs, we'll be able to solve this equation algebraically. We'll get the exact answer. And oftentimes it's quicker to do this than actually to go find a graph on a calculator. So first thing to do is to isolate that e part. So we'll divide both sides by 40,000. And we'll go ahead and reduce and just get 5/4. And then here's where we're going to take advantage of our log properties. We're going to take the log of both sides. Perhaps the most important thing we're going to do today. Take ln of both sides. You could take log with any base. Hopefully we'll see why ln is a good choice. I mean, ln has to do with e, that number that's about 2.718. And we're going to take ln of both sides. So I'm going to rewrite that blue equation. And leave a little space in front of both so that I can put in ln. So we go ln of this thing equals ln of this thing. And as long as you do the same thing to both sides, the equation is still legit. So let's go back. We're going to make use of what I said was the most important property of logs right now. This says ln of e to something. ln of e to something. Let's go back a page. See if we can find a property that says ln of e to something. Here it is, ln of e to the x. ln of e to anything is equal to just whatever's up there. In a very real sense, ln and e cancel when they're right next to each other like this. You just get the power. So here, ln and e cancel. I'm going to cross them off. And the left-hand side just becomes 0.013t, much easier. And that's how we handle solving an equation where the variable is in the exponent. You take a log of both sides. Could be a natural log, could be any log. And in doing that, you're going to be able to make use of the property that even if things hadn't canceled nicely like they did here, we still have that other property that says when you have a log of something to a power, you move that power right down to the front. And we'll do that in the very next part of this problem. So last thing is to solve for t by dividing both sides by 0.013. And that's it. So we can type this onto the calculator. And let's see how we do. So this should give us the number of years it takes to grow from 40,000 to 50,000 people, a little over 17 years. Okay, now we're going to answer the second part of the question. It said, what if the population grows compounded annually instead of compounded continuously? So before we do any of the equation hunting, make a guess. Write down a guess. Is it going to take more or less than 17.16 years? The second part of the problem. Population is going to grow annually instead of continuously. Pause the video, make your best guess, and then come back. All right, hopefully we reasoned through and thought about the fact that the more often you compound, the more the effective rate. So the most a 1.3% rate will ever be is if you compound continuously. That makes it the most in terms of its effective rate. So anything else will be not as large a growth rate. So compounded annually, it's not going to grow as quickly as it does here. And so how long will it take to get to 50,000? It will take longer because it's not going to grow as quickly. So we're expecting some number bigger than 17.16. We don't know how much bigger, but definitely expecting bigger. Okay, so when it's not continuous, we're using the other formula that we had. A is equal to P times 1 plus R over N to the NT. And so in this case, A is equal to, so the P is still 40,000. That's how many people we start with. 1 plus, okay, the rate is still 0.013. Divided by n. How many times is interest compounded annually? Just once. This thing is compounded annually. So n is 1, and the n up here is also 1, and then that's times t. So in actuality, we could have used the simpler version, 1 plus r to the t. That would have been just fine, because in this case, n is 1. And so when you plug in n equals 1 here and here, you just get this simplified version of things. Okay, let's clean this up just a little bit. So that means that 40,000 times 1.013 to the t is our formula, and we're hoping to make this thing equal 50,000. So we'll put a 50,000 equals over here. Still trying to solve for t. Still going to divide both sides by 40,000 first, and we'll reduce. And now we're going to take the log of both sides. Now the natural log isn't the natural choice anymore, because this problem doesn't involve e. So should you use common log? Sure. Could you use natural log? Absolutely. Could you use log base 7? Why not? Well, there's a reason why not. There's nothing wrong with using log base 7. The only problem, practically speaking, is that you are restricted to just these two log buttons on your calculator, log and ln. You got no other log buttons on the calculator. So using log base 7 would require work just because of the technology. So let's use the common log just to try something different. I'm going to write that equation again. 5/4 equals 1.013 to the t, leaving a little space in front so that we can take log of both sides. This time we'll use log instead of ln, but it makes no difference really. All right, but here's an important moment. Don't have this nice thing where log and 1.03 cancel in the same way that ln and e canceled, but we do have something that says log of somebody to a power. Log somebody to a power. Let's go back a page, see if we can find a property that says log of something to a power. It's down here in part F. Log of something to a power. What can you do with that power? You can bring it to the front. Bring the power down to the front times copied log. So you pick that power up, physically move it down there, and that's it. So let's do that. Might not be clear why that's going to help us solve for t, but let's do it anyway. I'll copy the left-hand side. Log of 5/4 equals, we're going to bring this power down in the front. T times, you don't need to write that dot, log of 1.013. So here's the good news. The variable is no longer in the power. Being up there in the power, it's kind of difficult to access. But the variable is now down here, very accessible. That's the power of logs. So other good news is that log of 1.03 is just a number. You could type it on the calculator if you want to, but in my mind, I'm just thinking, oh, okay, this is like the number 14. And so really the equation is saying 14t equals some other number. And how would you solve that equation for t? You'd divide both sides by 14. We're going to divide both sides by that log of 1.013. And so our answer to this question is just log of 5/4 divided by log 1.013. And that's it. We can type this on the calculator. Remember, we were expecting that the answer was going to take, that this one would take a little more than the 17 years because we weren't quite growing as quickly. So we do log of 5/4 divided by log of 1.013. More than 17.16 years, yes, a little bit longer, about another 1/10 of a year, about a month extra. Okay, again, the basic idea there, if your variable's in the power, you're going to use logs. Number 8, here's some more complicated equations for us to solve. Basic idea is to isolate the exponential part and then use logs, or isolate the log part and then rewrite the equation in exponential form. Part A, 15e to the 0.02 equals 20e to the 0.01t. I think I didn't read the t on the left-hand side, but there's variables on both sides in both powers. So what can we do? Well, I would really like to get these e's together on one side. So on the one hand, I could subtract and end up with something like, you don't need to write this, but something like e to the 0.02 minus e to the 0.01t. There'll be a number in front of both, right? 15 there and 20 there, and that's equal to 0. Where do I go from here? Is there a nice rule to combine e's with different powers when you're subtracting? The answer is no. Technically, you could proceed from here and factor, and that would be kind of equivalent to what I'm going to propose. But I'm going to suggest that instead we divide. Divide both sides by, it hardly matters. I'll divide by e to the 0.01t. And so on the left-hand side, we get 15 e to the 0.02t divided by e to the 0.01t equals 20. So the good news is at least the e's are together. And the better news is that there is a property that tells you how to handle e to something divided by e to something. I'll just remind you of maybe a more familiar looking way to see this property. X to the a divided by x to the b. Keep the base, subtract the powers, top minus bottom. Well, that's exactly what we have. E to a power over e to a power. We're going to keep the e just as it is, and we're going to subtract the powers, top minus bottom. Okay, so this becomes 15, we'll just copy that, e to the, and now we're going to subtract those powers. I'm going to write all the detail here, 0.02t minus 0.01t. That's the new power, whatever that is, equals 20. 15e, and then we'll combine terms, 0.01t equals 20. Good. We did a lot of work. We got the e's that were on both sides, and now they're just on the one side. Trying to solve for e. One of the hints up here in the setup said maybe isolate the exponential part. So what do we want to move away? Well, we're trying to isolate that piece right there. So move the 15 out of the way by dividing both sides by 15. So we get 20 over 15, which reduces to 4/3. And now how do we handle it? The exponential part is isolated, it's all by itself, and the variables in the power use logs. Common log or natural log. In this case, natural log is much better because of the appearance of e. Nothing wrong with using common logs, but it's going to take an extra step to get to the answer, so may as well get there quicker. Copying my equation and then putting ln in front of both sides. And the good news is ln and e cancel when they look like that, so the left-hand side is just 0.01t equals ln of 4/3. And then the final answer, divide both sides by 0.01. Moving on to part B, log of 3x plus 4 equals 3. This one is going to be quite a bit easier. We just need to use the definition, converting the log into the corresponding exponential equation. I'll write the invisible 10 down there. I'll write it in a different color. And then we're just going to follow the football play. 10 raised to this power, copy the equals, and then whatever is in the parentheses. So we say 10 raised to the third equals 3x plus 4. 1,000 equals 3x plus 4. Subtract the 4, we get 996 equals 3x. And then divide by 3. And we get x equals 332. So if you have an equation with log in it, and the log is the only log that appears, just try to use the definition of logs and get that log to be written in the corresponding exponential form. So number 9, remember if you're solving an equation where the variable's in the exponent, isolate the exponential part and then use logs. Next page. Number 10, here's a brief history lesson from the wonderful and very readable book, E, The Story of a Number by Eli Maor. This book can be requested at the GCC library. They will deliver it here for you from another library. So let's see, logs are invented by John Napier, 1550 to 1617 from Scotland. He invented logs to ease the burden of calculating with really big or really small, close to 0 numbers. As the mathematician Pierre-Simon Laplace said, by shortening the labors, the invention of logarithms doubled the life of the astronomer. Astronomers had to spend quite a bit of time in their working careers just doing massive calculations. Way back when, they didn't have calculators, so they had to do all these calculations by hand. And with these huge numbers that astronomers were dealing with, they would spend a lot of their professional lives just doing calculations. Napier comes along, invents the logs basically out of the blue, and it shouldn't be clear to you why that makes it easier to do calculations with big numbers, but it turns out it does, and he essentially doubled the life of the astronomer. Napier spent 20 years calculating logs by hand, 20 years, making something that essentially does what this calculator does when I type in something like log of 94.5. Napier did a lot of work to try to figure out a good estimate for that number. We've got everything now in the calculator. Napier's definition of log differed slightly from the present day definition, which was introduced in 1728 by Euler. The activity for today is in your textbook. It's these 4 problems from pages 186 to 187. The problems are also below. The learning objectives follow these problems, and of course you can take a look at the video for this activity, but I'd encourage you to spend a good bit of time working through this activity before you go to the video or the PDF with all of the notes filled in.